for flight school. Me too. Let's go.
Welcome everybody to Brendan's Flight School. I thank you all for coming. Today, we're going to talk about the four forces that act on an aircraft. First, we have our lift. Second, we have our drag. Third, we have our thrust. And fourth, we have our weight. Yes, Elmi?
Can you show a vector diagram for that?
Indeed I can. So, if this is our plane, with the nose facing this way, this is our little engine right here.
Okay.
Our thrust is going to be going forward, sort of like our applied force. Our lift is going to be acting upwards from the plane. Our weight is going to be acting in the direction of gravity. It could be seen as the force of gravity. Then our drag is going to be acting backwards away from our thrust. So this is our force of thrust. This is our force of lift, or can be also seen as the coefficient of lift. This is the force of weight / force of gravity, and this is the force of drag, or the coefficient of drag. Quickly, we're going to look at the different axes of an airplane. Running right down the center, right through the center of gravity, we have our normal axes. Moving around this is called yaw. Going from wingtip to wingtip, we have our lateral axis. Moving around that is called pitch. Then, from the nose of the plane all the way to the tail of the plane, we have our longitudinal axis. Moving around that axis is called roll. Yes, Kendall?
How do you find the lift and drag of an airplane?
Well, for that we have two simple formulas. For lift, we take the coefficient of lift, multiply that by 1/2 the pressure of the air, times that by the volume of the air squared, times the surface area of the wing. For drag, we take the coefficient of drag, times that 1/2 the pressure, times the volume squared, times the surface area. So, as you can see, these two formulas, exactly the same, just taking the different coefficient of lift and the coefficient of drag to find your lift or drag. Yes, Ami?
How is lift even created?
Well, Ami, when we look at an airfoil, you have a camber on the top. What this does is it causes the air to move faster as it goes over the top, creating a low pressure. The air moving below is going at the same speed it would be, creating relatively high pressure. This causes the air to want to push up towards the low pressure, creating lift. Now, Ami, if you want to open to page 15 of your From the Ground Up, we're going to look at a little section. Good job, Ami. Air flowing around an airfoil is subject to the laws of motion discovered by Isaac Newton. Air, being a gaseous fluid, possesses inertia, and according to Newton's first law, when in motion, tends to remain in motion. The introduction of an airfoil into the streamlined airflow alters the uniform flow of air. Newton's second law states that the force must be applied to alter the state of uniform motion of a body, correct?
Correct.
The airfoil is the force that acts on the body, in this case, the air, to produce a change of direction. The application of such a force causes an equal and opposite reaction, Newton's third law, called, in this case, lift.
How did they ever figure that out?
Well, Kendall, there was a wonderful scientist named Bernoulli that created the Venturi effect, or investigated the Venturi effect by using a Venturi. What he figured out is that when you constricted the passing of a fluid into a smaller piece, so when you look at our Venturi, into this piece here, it created a lower pressure. So there was a lower pressure system in the center of this constricted passage than there was out here, where there was a higher pressure system. The reason for this is because the water, or whatever fluid or air, was forced to move faster through this constricted piece, causing the lower pressure.
How does that even relate to planes?
Well, Kendall, what this showed is that in that tiny little piece of that venturi, he was able to realize that an increase in speed of any fluid, and let's remember that air is technically considered a fluid, caused a lower pressure. So he was able to create the Bernoulli's principle, which states that an increase in speed of any fluid, air or otherwise, is going to create a lower pressure. And that's how the theory of our wings create lift.
Okay.
Today, we're going to talk about couples.
But I don't have a boyfriend.
Okay, so when we look at our couples, if we're looking at lift being behind weight, if we see that as pulling two strings, pulling the lift string up and pulling the weight string down is going to pull the nose down and the tail up, correct? Well, if we look at the weight of the aircraft behind the lift of the aircraft, so when lift is greater than weight, the nose is going to be pulled up if we see that as two strings acting on the aircraft. Now if we look at our thrust and our drag, if thrust is above drag, that's going to cause the nose to point down. Well, if we look at thrust below drag, that's going to cause the nose to go up. Okay, now we're going to talk about relative airflow. What relative airflow is it's basically the relative wind as your plane or object is moving in a direction. So when you walk and you feel wind against you, there may not be actually any wind, but the relative wind based on your motion is your relative airflow. My movement through the air is causing a relative wind against my body. You better take a moment to explain what angle of attack is. When you look at our lovely diagram of our plane here, right through the wing from the trailing edge to the leading edge of the wing, you have an imaginary line called the chord. That continues to go all the way in front of the wing. The angle that the chord makes with the relative airflow is called your angle of attack. So it's basically the angle that your wing is making with the relative airflow is your angle of attack. And when your angle of attack is exceeded, that's when you start to have problems like stalls. We're going to look at how the different forces of the aircraft act on the said aircraft in the different stages of takeoff. First, we're going to look at the taxi, how we get to the runway. At this point, our FG is acting on the aircraft. FG equals mass times gravity, and our Fn is just going to be the opposite of Fg, so Fn equals Fg. We do need a little bit of thrust just to keep the airplane moving at this point, but not enough to make any lift, so we don't have a force of lift at this point. Our F thrust is being counteracted by the force of friction of the wheels on the ground, which our force of friction is mu Fn, so it is in relation to the weight of the aircraft as well. When we look at our ground roll, we can see a couple similarities in our vector diagrams. Our FF is going to be the same due to the fact that FF is mu mg, and the weight of our aircraft really hasn't changed. The thrust is going to start to increase as we want more air moving the airfoil to create lift. Our Fn is going to start to decrease just a little bit just because we start to have some lift acting on our wings. Our Fg is still going to be the same as we still have force on the ground. We can also look at it through a couple different forces. We still have our thrust, which is increasing again because we want to create more lift through the airfoil. But now we have our lift. Our lift is going to start increasing as our thrust increases as the more air passes over, and this is going to allow us to lift off the ground. As we're starting to lift off the ground, our Fn is going to decrease. And once our wheels get off the ground, we have no more friction. We don't have a coefficient of friction anymore because our wheels aren't interacting with the ground. We have our drag. The drag is going to be created by the plane moving through the air. You have a couple different types of drag. We're not going to get into that. It's just going to be the aircraft's resistance to the relative airflow. Next, we're going to look at the forces during the period of rotation. This is when the pilot is going to start to pull back on their control column and the nose is going to start going up and their angle of attack is going to start to increase. At this point, our lift is starting to increase as our thrust is at its maximum point. We're getting a lot of lift on the wings, enough to overcome our force of gravity at this point. So we're lifting off the ground. Our drag is also increasing. Since our speed is increasing, the pressure of our aircraft are creating more drag. Our thrust is no longer just on the x-axis, since we do have our angle of attack, which is the angle at which the wing makes with the relative airflow. So again, like we had talked about, our relative airflow is the airflow relative to your plane's direction. So our thrust is now split up into an X and Y component. Now we're going to look at the general vector diagram for landing. When we look at this, first thing we notice is that our thrust again isn't acting solely on the x-axis. It is again acting at an angle, since when you land you do have to direct your nose towards the ground. And so your thrust is going to be split up into the x and y components again. Then when we look at it, we still have lift. We still have some lift to stay in the air. We're not just dropping like a rock. And your drag as well is, you still have your drag since your plane is still moving through the air. Moving through a fluid, you still have that resistance. And then force of gravity, always going to be constant since Fg is mass times gravity. First, we're going to take a moment to talk about flaps. Flaps are a control surface that extends from the trailing edge of the wing. What flaps do is they're high lift devices which in effect increase the camber of the wing, and in some cases also increase the effective area of the wing. Their use gives better takeoff performance and permits steeper approach angles and lower approach and landing speeds. Now we're going to talk about how flaps affect our different forces during landing. So when the pilot increases the flaps, the purpose of this is to be able to slow the airplane down and use the airplane effectively and efficiently and without a risk of crashing or stalling at lower speeds. So in relation to flaps, increase the lift of the aircraft, but also there's more wing for the air resistance to hit, so it's also increasing the drag of the aircraft. Now class, we're going to look at spoilers. Spoilers are devices fitted to the wing which increase drag and decrease lift. They usually consist of a long, narrow strip of metal arranged in spanwise along the top surface of the airfoil. So what that means is, if we were looking at our airfoil, so this is our side view of the airfoil, if we were looking at it from the front, say this is our nice little arc, it would come up like this. The purpose of the spoilers is to spoil the lift going over the wing. As the lift is trying to come over the wing, it's going to hit this and just become a jumbled little mess, and you're not going to have no lift. So this is mainly what gliders use to get down to the ground. It's also used on many commercial jets as well as Cessnas just to help bring it to the ground. Now we're going to talk about what spoilers do to our vector diagram or our different forces during landing. So again, we're going to look at mainly our lift and our drag, because our spoilers aren't really going to affect our thrust, and our Fg is always going to be constant because again, Fg equals mass times gravity. So when we pull our spoiler bar, pop the spoilers out of the wings, what that's going to cause is that's going to cause the lift to decrease sufficiently. So at this point, we are falling. We still have some lift, so we're not dying, but we are falling. This is another piece of area popping out of the wing for the drag or for air resistance to hit, which is again going to increase our drag. Which in this situation when we're landing, we want to slow down, we want to land safely. That's not necessarily a bad thing. Next class, we're going to talk about speed brakes. Speed brakes are a feature on some high performance aircraft. They are designed to facilitate optimum descent, but without decreasing the power of the aircraft. This is for the ability to shock cool the engine. So if we're looking at our front view of the wing, speed brakes are going to pop up like that. They're going to decrease the lift, as the lift isn't going to be able to be produced over the wing, but it's not going to cause any more drag or decrease the power of the aircraft. So then if we look at our side view, it sort of comes up exactly like the spoilers. Now we're going to look at how landing with speed brakes affects our lovely little vector diagram here. When we pull the speed brakes out of the wing there, our drag increases sufficient enough amounts to slow our plane down, and that's why they're called speed brakes. Yes, Kendall?
Why does it not affect the lift?
Well, remember when we were talking about speed brakes? The speed brake sort of had a shape like this with two holes in it. That allows the movement of air through it, and since that's sitting on the top of the wing, that still allows the lift to be created on the wing, so the force of lift really isn't changing.
We're not putting volume to this, right? No, but the candles need to do landing. The candles need to do landing. If your thrust is pointed upwards. No, stand back away from the candle and like scrunch your hair. I only like scrunch your hair, but you can't really like. That's really like drama.
Maybe if you weren't late to class every day, you'd know what I was talking about. Kendall didn't even finish hers. Congratulations, you now know the basic physics of planes taking off and landing and how the different control surfaces affect those forces.